Swayam Prabha. Digital India. Educated India.
What if the valuations are identical? No, then what will happen? Okay, let's see if we understand. So say I'm a special case where all the valuations are identical for all the agents. Like VI is equal to VJ for all INJ. Certainly not a very interesting case, but say if I have that and I run this algorithm, what will happen? What is that? Exactly, everyone will shout at the same time, right? When you move the knife, the value of 1 over n is achieved exactly at the same point for everyone, right? It's the identical valuation. So all marks, all the xi's will actually, x here will coincide every time. So you'll pick one of them arbitrarily, assign it, move on. In that case, do I get a proportional allocation? Is that obvious? It's not too... Okay, let's very special case, very simple case, before actually we jump on to more general constructs. Say I'm in a world where in a cake cutting scenario where everyone has the same valuation, right? What will end up happening is that when I move the knife, when I execute this algorithm, this xi will always be the same for every agent, right? Like wherever you are, like, so if this is of value, say you're here, L, there's some number of agents left. If for some agent xi, this interval is of value 1 over n, the fact that the valuations are identical means that this interval is again of value 1 over n for everyone else in W. So the xi's always coincide, right? But now notice that what's happening is that the first agent that goes away gets a value of 1 over n. That's by design. I star is kind of happy because this interval was exactly of value 1 over n to I star. That's why I star shouted. But you're always removing a value of 1 over n, 1 over n, 1 over n. So in fact, everyone else ends up getting 1 over n. There are n agents. All of them get 1 over n. They have identical valuations. The valuations are additive and normalized. There you go. Right. So if that's not clear, let's go over it one more time. If it is, I'll try to move to a general proof. Yes? No, we are following the algorithm that's written in black and blue, white and blue here, which is that I start off with so think of it as like a mediator implementing it in contrast to cut and choose, but whatever. So the idea here is that I start with L equal to 0 and I'll keep moving. So again, this algorithm is quite explicit. So all I'm saying is, let's just read it as a pseudocode. For every iteration, I'll ask each agent to give me this xi, right? And I'll pick the one that is the leftmost. So argmin here, this is the leftmost mark. If argmin is sort of confusing in particular, so I've run the algorithm, I have some value of L was 0, but now like I look at all the guys that are in W, everyone tells me like xi is here, xj is here, xk is here for different agents. I'll pick the one that has the leftmost mark, say k, and k gets this interval. The fact that this is of value 1 over n to k is by design, and this is right here. And so this agent is happy, right? And then I give this to ik, I push k out of the waiting list because it has already received the interval, and I update L to here and I repeat. So there's no cut and choose per se, it's just cut and assign. Move your knife, assign, boom, boom, boom. My claim to you is that this simple case where all the valuations are identical, you are good to go, in the sense that everyone will get exactly interval of value 1 over n. Because when the first time everyone shouts, like x1, x2, x3, xn will be some identical, you give it to x1, right? You have moved one agent out, but the remaining cake is of value 1 minus 1 over n, so on and so forth. Right? So if the valuations are identical, it's sort of the execution of the algorithm is sort of simple to follow, and so gives you proportional cake division. What I'll do next is sort of argue that this is actually true in general. Even when you have distinct valuations, this algorithm ends up assigning a proportional allocation. And let me just complete it by saying that yeah, there's no other one. It has to be exactly that. Yeah. So the question was, if the valuations are identical, how many proportional allocations are there? Well, n factorial. Right? You can assign one and permute it. Like the permutation won't change. In fact, that's exactly the NV-free ones as well there. So what's not obvious about it? Like what is the sort of trick? Like what's the subtlety in arguing that this thing always finds a proportional allocation? What's the, like what essentially do we have to argue to sort of show this proof actually works? What is that? Yeah, I mean, among other things, at the last, in fact, I mean, it does run to completion. That's one aspect. I mean, what's not obvious right now is that we don't end up in a scenario where the cake that is left is of value less than 1 over n for all the agents in W. Right? It's not the case that you have actually over-assigned things. And this is exactly where the selection rule comes in. I'll write down a proof just to be specific, but the argument is really pedestrian. All it's saying is that, look, every time you are keeping me in the waiting list and assigning it to someone else, with respect to my value, you are not giving away more than 1 over n. Right? Why? Because whoever remains, the xi's were greater than equal to xk. Right? So for these guys that did not get a piece, these guys who were still kept waiting, this chunk was not of value at most 1 over n. Right? So you moved away one agent, you gave away something that was of value less than equal to 1 over n to me. Again, you gave another piece to some other agent, but again this was of value less than equal to 1 over n to me. So overall, it will never be the case that you have sort of given, if the k agents removed, the value that has been lost is sort of not high enough, and which essentially means it's not more than k over n, and whatever remains is sufficient to argue that this algorithm will run to completion. In particular, it's sufficient to argue that the last guy, the chunk of the cake that remains, is of value at least 1 over n. I'll do it specifically, but I just want to sort of ease into the fact that really the argument isn't something, there's no fancy math, it's a high school, if not less, level argument. It's a very fairly, and once you have the algorithm, the argument is quite clean, quite simple. And again, something for your notebooks, whenever you have an existence result, try to pinpoint the where does this existence argument, what's the root of it. And here the root is a potential argument. Right? It's a potential which is saying, okay, you're removing one agent, you're removing part of the cake, but the value that remains for any agent for the remainder of the cake is high enough. Right? So it's a sort of, in that sense, the underlying, the totality here, the existence argument here comes from a potential argument. So again, let me prove it a bit rigorously, but yeah, if you understand this claim that if I kick out one agent, whoever remains, the value lost is less than 1 over n, so you are good to go. So here's sort of the so whenever you have this kind of a thing that, okay, some good properties continues to hold, I mean, your friend is induction, right? I mean, you just argue inductively that this holds. Again, this is more for the sake of doing things properly. If you understood the previous discussion, it's just sort of pretty much just making that observation rigorous. So I kind of run the algorithm and I have this iteration count k, which is the number of agents that have received a piece, received an interval so far, right? So you're running it, you give it to 1, give it to 2, so on. So the k is this iteration count that keeps on growing. So if here, what will be the cardinality of set w? How many agents will be waiting? If I, okay, you see, I'm running this algorithm. At some point I stop it at the end of the while loop. At that point of time, I have assigned pieces, intervals to k agents. How many agents remain? N minus k. Right, so, right, I've given it to k. Whoever I've assigned, I kick it out of w, right? That's the sort of algorithm. I mean, if there was space, I would have written it here, but I hope the algorithm is sort of simple enough to, like, you can refer back to your notes, but whenever I assigned, I kick it out, so this is exactly n minus k. This is an observation, but the invariant that I'm going to argue holds inductively is that, so say this happens, so what is k at the beginning? What's the base case of this induction? 0, right? No one has received anything. But the claim is that so for all agents in the wait list, in the set capital W, if I look at the value that agent A has for the leftover thing, so again, L is the cut point at the, when I stop this algorithm while it's running. My claim is that this is at least what? So note that k is never going to be more than n minus 1, right? This essentially means that when k becomes n minus 1, the loop sort of terminates, I go out of it. So k is n minus 1, which essentially means that this thing, the right hand side here, is always more than 1 over n. Right. Is that is plugging it in. So again, this is sort of just restating the observation we made in a bit more rigorously. So when one agent gets assigned an interval, k is 1, whoever remains in this set W, the value of the cake, the remainder cake, which is this thing, I update L, is 1 minus 1 over n. It's still quite large. Right, when two agents go away, it's 1 minus 2 over n. It continues to be large enough till all the n minus 1 agents. In particular, when the loop terminates, there's exactly one agent left, i.e. W, the cardinality of W is exactly 1. K is equal to n minus 1. Note that this holds, the second part, this holds with equality. So even for the last agent, whatever remains, right, this last agent here is, if I prove this claim, what I have is that even for the last agent, the part that it receives is sufficiently large. It's 1 over n. Okay. What is that? L is the current, yeah. So, I mean, say like I1, I2, again, this indexing is sort of is slightly overloading, abusing notation. It's not necessary that the agents will get the piece in this order, but whichever k agents got a piece, let me just call them I1 through Ik. So these things are gone, right? Like in particular, like I1 was here, I2 was the second agent, and now Ik, so say it was this. So L is right now here, so this thing is exactly equal to Va of, I look at the whole interval, but now this entire chunk has been sort of assigned away, it's gone. So I remove these intervals, whatever remains, this is the part that still is unassigned. This part for an agent A that's still waiting is large enough. I'm claiming that this is continues to be 1 over n. It's actually sometimes better to prove a slightly stronger inequality. It helps in induction. So I essentially want this thing, but I'll prove a stronger one because, again, it sort of helps in, this is sort of a common phenomenon in induction that you need to sometimes have the right inequality to induct over. This is a very simple instantiation of that observation. But note that once I have this, I'm good to go. This proves that the algorithm will succeed, will successfully find a proportional allocation. Okay, so can someone quickly tell me why this is? So base case is fine, k is 0, w is all of n, and then this just says that your total value is equal to 1, so it's at least 1. So base case is golden. What's the inductive argument? So assuming it for k, can you argue it for k plus 1? So exactly where the selection rule comes into place is exactly where I use the fact that the cut is made at the assign it to the leftmost guy. So what nice property of the valuation do I use here? Yeah, so it implicitly uses the fact that the valuations are monotone. So if you are giving a, so for all A and W, so I look at all agents, this was the current value of L, this was XA, and this is XI star. So I star is the agent that receives an interval in the current iteration. This is the K plus 1th agent, if you will. So this interval goes away, right? But note that for A, this is of value 1 over n. So by monotonicity, which is a consequence of the the additivity and the non-negative property that we have assumed, this thing, the thing that you kind of remove, is of value less than equal to 1 over n, right? So for these guys, VA of LXI star is less than equal to 1 over n. Hence, by induction, this kind of continues to hold. L was here, now you update it to here, but so what you do is like VA of, so say the new L, this thing that I'm subtracting out is of value less than equal to 1 over n by selection rule. So this is greater than equal to, so this again by inductive hypothesis I know that this is k by n, this I know is at most, it's a negative sign, so be careful, but again this gives me what I want, so sort of continues to hold. Again, sort of looks a bit messy, but the idea is quite simple. I'm just chucking off a piece of that was, you didn't claim it, which means this was a value at most 1 over n to you. Fine, then wait, one agent has dropped, you still have enough opportunities in the remaining case to sort of get a proportional share. Okay, so few observations. First one is that note that if an agent honestly follows this algorithm, that then it will receive a piece of value at least 1 over n, right? So as long as you are being honest about your marks, the cuts, you're guaranteed to receive a interval of value at least 1 over n, irrespective of what others do. Furthermore, if your input is like a piecewise constant valuation function with rational breakpoints, then you can argue that the output of the algorithm, these cut points, will also be rational. So this proves that for a rational input, by which I mean an input where the valuations are induced by density functions that have rational breakpoints, there exists a proportional division. Not just that, there exists one where the breakpoints are rational. So this, again, two sort of observations, again, sort of you can offline go over them and verify that these two facts are correct. Okay, excellent. So what we have done is actually managed to prove that there's an efficient process. In particular, if I give the valuations as explicit input, say the densities as explicit input that induce these valuations, so polytime algorithm, right? My question to you is that say I work in a model where I actually do this thing in a query like setup. So at every time, in every iteration, when I interpret this step as literally asking the agent to tell me what xi is, right? So I go to this, for every agent I ask this. So now with this sort of query interpretation, where you have n agents sitting in the room, I'll ask everyone mark, and I'll find the leftmost mark, give it to the first agent and say, okay, you're done, walk out of the room, iterate it, and someone tell me how many queries I'll make. What's the query count of this moving knife procedure? What is that? N into? Yeah, it's theta n square. Right? Yeah. So why is this? Well, you just look at the cardinalities of W, it's decreasing by 1, and every time you run it, you actually ask every agent in W to sort of tell its mark, right? So initially, so you ask n queries in the first round, n minus 1 queries, that's the size of the wait list, the set of agents that still haven't been assigned a interval, yada yada yada, to 1, which is exactly theta n square. So that's the sort of number of efficient but quadratic. Okay, like a good computer scientist, the question is this the best we can do? Can we push the envelope a bit more? So note that if the valuations are piecewise constant, that is, if I have density functions, then I can give them as explicit input. But if I sort of step back a bit and only look at valuations that satisfy the 3 properties I need, then it's not obvious if there's a specific model wherein I can give them as explicit input. Right? These are defined for infinitely many intervals. So even with additive valuation, it's not obvious whether I can give it to you, give this as an input. So sort of the right complexity model to study cake cutting algorithms, to sort of identify the efficiency for a bit more general valuation class, is to in fact look at the query count. And this is a very natural measure when you are interacting with agents. Right? You have n people, you want to divide something fairly among them. It's kind of natural to ask them for their valuations as you successively make allocative decisions. So this query count is a natural measure, and it's sort of formalized in this model called the Robertson-Webb model, again proposed not surprisingly by Robertson-Webb. So So again, the point is that there might not be a finite discrete representation of a cake cutting problem instance, and this is the concrete complexity model we sort of adopt to specify the number of operations required in a cake cutting algorithm. It's a query complexity model. So what is the model has two very natural sort of, how do you interact with the valuations? Well, think of it as you have n agents and their values are somehow specified as a black box, and you can query every agent about its value. How can you query them? There are two types of queries. The first one is simply an evaluation query. So this So idea is you ask an agent A, okay, here's an interval, the left point of this interval is x, the right point of this interval is y, what's your value for it? So it just looks at 0, 1, xy, you query the agent replies with a number, the number is exactly this value, right? Its value for this interval xy. The second type again is of the form x alpha, and this sort of now returns a mark z, a point z. So you have a target value alpha in mind, and you ask the agent, okay, if I start at x, and if you want to achieve a value of alpha, where should I cut it? So this is the target value alpha, and VA should achieve this target value within this interval. If there is no such mark, say agent returns like a null or some standard convention. So my claim to you, okay, which kind of a query will I need to run my moving knife procedure among these two? What is that? The second one, right? So I'll call the second query with what value of alpha? With what value of x and with what value of alpha? What is that? -2. Huh? The answer was I would run the second one. If I want to run this algorithm with this query model, what is the value of x and what is the value of alpha? It's a very trivial question. X is L and perfect, yeah, very simply. I just want to know exactly the value of 1 over n. The mark, finding this mark is calling this second query with x as L, the current value, and alpha as 1 over n. So the point is that if I work in this specific Robertson-Webb query model, I'll need order n square, theta n square number of cut queries to actually execute this algorithm. And the follow-up question is, can we do better? Right, and when you have the first follow-up question, the answer is typically yes, and here it is. So this is the algorithm by even in paths. I will try to quickly cover this and then we'll break for lunch. But okay. So it's a recursive method, and so what we'll do here is sort of assume that the total number of agents, the number of agents for whom I want to find a proportional division, is a power of k. is the power of 2. I'm just doing this for ease of presentation. None of the arguments are like critically based on this assumption. Okay, so as I said, this is a recursive process, and the idea is each successive call to this algorithm, I'll actually I'll invoke each recursive call with an interval xy and some set of agents that, again, W, in the sense that these are the set of agents that would want to receive a piece in this interval. So I have 0, 1, I'll invoke this recursive call with an interval and some set of agents W who are in the end going to receive an interval which is sort of contained in this scenario, right? So what's the recursive call? Well, if there's exactly one guy contesting for it, you do something very obvious. You just assign so if there's just one agent contesting, you just give the whole interval to this guy. Otherwise, you just again recurse in the following manner. So what you'll do is, like, for every agent that's contesting, that's still in this waiting set capital W, you ask for a mark ZA such that this subinterval x to ZA is of value half of the total value of the interval. So this guy just does in some sense what Abraham was doing, boom, marks a point, and you do it for every agent, right? So how many, like if I look at the query model, how many queries do I need to execute this specific recursion call? What do I need? If I look at this query model, I have access to these two queries for every agent. How many times? So okay, for one specific agent A in this set capital W, how do I find this ZA in that, if I have access to those two queries? What is that? For one specific agent, let's just start. I have one specific agent A. I want to find ZA. How many queries do I need? Queries of the two form that I have specified. Okay, yeah. 2, would that work? So first of all, I need to find this value, VA of xy, right? That's one eval query, right? I'll invoke, literally I'll invoke eval for agent A and xy. Now I know this value VA of xy. I have it, that gives me alpha, and then I invoke this cut query with that x and half the value. So I'll need 2 queries for every agent. So how many total? If the size of W is 10, I'll need 20 queries. I'll need 2 times W queries to sort of execute this step so far. Okay, and now how do I recurse? So, okay, the idea is I have xy that W many agents contesting for it, everyone gives me a mark, so this is ZA, ZB, so on and so forth. And what I'll do is I'll keep looking at these marks and find the one, Z star, such that half of the agents have marked, their mark is on the left of Z star, and for the other half, half the agents have marks here, and the other half of the agents, the marks are here. So I just sort these Z's that I have obtained for all the agents in the set capital W, sort them left to right and pick the n by 2th mark, right? So I keep going till pick the W by 2th mark. Since n is a power of 2, I can always that's why I assumed it's a power of 2. I'll always have exactly a unique median. Okay, so with this I recurse on. Yeah, those tie-breaking rules I'll not specify. I mean, if you have this, if you have the question of how do I tie-break, you should have also figured out the answer of how do I do that. It's always arbitrary. Like it's hard for me to come up with an example where some non-trivial tie-breaking rule is required, at least for these lectures. Right. Right, so if you have identical marks, you do an arbitrary partition. You just pick, again, you pick W by 2 of these agents and call the recursion on the left and remaining on the right. So this is the median mark. So W by 2, half of the agents contesting have the marks left of Z star. There's some agent that is at Z star, but the other ones are to the left of it. So you recurse on this, so just call this with x Z star and those subset of W that of cardinality half that sort of made these marks, and also you recurse on Z star Y, so you kind of recurse here and recurse here. I'm not being too sort of, I hope what the meaning of left half of agents and right half of agents is clear. It's just agent ZA, whose Z is less, goes in the left half. If ZC is here, the mark is to the right, the agent goes to the right. Okay, so so if I look at the recursion tree, so at the root of the recursion tree, I have the whole interval, and W is just all of the agents. When I instantiate the algorithm, I just give the entire cake and all the agents are contesting for it. What ends up happening is that like there's some Z star that gets invoked for the first time. Half of the agents come here, the other half of the agents, the Z mark was on the right, so on and so forth. Note that what this essentially means, so this is again, and this will kind of keep recursing. So whenever I draw this line, I mean some interval. So this will be like z star comma, like z star 1, so to say. So let's say z0. So just kind of recursion keeps on. What's the depth of this recursion tree? Yeah, so this is the number of agents that are competing. Here there are n agents competing. When I split it by construction, half of the agents get called with the left half, half of them. So this is the number of agents competing. Here it's n by 4. What's the depth of such a tree? Log n. Right, every time it gets halved. Okay, so the key observation here is that whenever, again, inductively, and this is maintained throughout the recursive calls, so if I'm looking at depth k and I look at an interval that has been called, how many agents are competing for it? So this is depth 1, this is depth 2, so depth 0, the root, say following standard convention. So what's the, if I look at like depth k and I have an interval here, so how many agents are sort of contesting for that single piece in a recursive call? Right, so it's again like trivial exercise to argue that this kind of drops by a factor of 2, right? You're halving it, so it's n over 2 to the k. Quite like if you want to do it, just do it base case induction. And the sort of another property that holds is that like for each agent, so again, base case is quite simple. When k is 0, this interval xy that's been called is the entire cake. So your value is 1. Plug in k equals 0, this holds. Now every time, like if you have xy, if you look at one particular recursive call, this is z star. So if you are an agent that sort of you have made a mark here. That's why you kind of like ZA was here, which means that the value of this piece is at least the value of XZA, right? So you are an agent on the left, which means that if I look at XZA, this was half of your value for the whole thing. That's exactly how ZA, this cut was defined, right? You ask the agent to do this Abraham's cut, half and half. But note that since ZA is to the left, this whole thing is actually is greater than equal to, again, monotonicity. So again, by induction, this inductive hypothesis was 1 over 2 to the k, multiply out a half, so you get 1 over 2 to the k plus 1. So yeah, this again holds inductively. And finally, I mean, when you have to log in, what you get is a single agent, courtesy this equation, plug in k equal log n, 2 to the log n is n, you have one agent, and the value that you have for this piece following from here is at least 1 over 2 to the log n, which is 1 over n. So at the root of this recursion tree, everyone gets a value of 1 over n. Okay, so let me just actually argue to you that the query count is quite less. So we have already discussed that whenever I do this recursion, I have the cardinality of W is 2 times the cardinality of W. So here the W is of size n by 2, it's of size n by 2. Here the W's are of size n by 4. So if I sum the W's up across any level, right, the size is always n. Right, every agent gets asked 2 queries irrespective of the depth of the recursion tree. So it's 2n. So pick any depth, the agent is somewhere in the recursive call, and 2 queries are being asked to every agent. So the total number of queries is 2n, since the depth of this recursion tree is exactly log n. The total sort of query count, the number of cut and eval queries that you'll ask throughout the algorithm is 2 to the n log n, which is sort of notably better than n square. There you go, you have an algorithm with n to the log n query complexity. Okay.